the previous video, what we actually done is we solved, rather not solved, but we used the graphical representation of a curve to determine the nature of roots. In other words, we could tell whether the roots were real, that's when they touch the x-axis, if there is an actual x-intercept, or we saw that the we saw that the curve cut the x-axis twice, which meant it had two real roots, or it only touches the x-axis once, which means it has two equal roots, which is equivalent to saying it only has one root. Now, that was a graphical way. We looked at it graphically. In other words, looking at a parabola and seeing how the parabola touches the curve. What we're now going to do is we're going to solve algebraically. And we're going to determine the nature of the roots and determine the nature of the roots. Right. Now when I say nature of roots, all we want to know, is it imaginary or is it real? Has it got two roots? In other words, does it touch the x-axis twice? Or does it cut the x-axis only once? That's when the turning point of the parabola lies on the same curve. That's what we really want to know here. Okay, so let's do this the long way. Let's solve, right? And remember, when you solve for roots, when you solve for x-intercepts, all you need to do is you equate the function to 0. When you solve for x-intercepts, we make f of x, or the function value, equal to 0, and then we solve for the x values. And we use the quadratic strategy for doing this, right? Or if it's any other curve, you just solve algebraically and you see what you get. Okay, so let's look at the first question. So the first question was x squared minus 6x plus 9. Now remember, if this is a function, I can represent and call the function f of x is equal to this. Now in order to solve this, I need to equate f of x to 0. So I say x squared minus 6x plus 9 is equal to 0, right? Now that is already in standard form. This is a quadratic in standard form. It looks like this. Standard form looks like this, where we say ax squared plus bx plus c equal to 0. So there's my a value, which is invisible 1. The negative 6 is my b value, and my c value is positive 9. And I've got equal to 0 because that's part of the standard form. Now, the first way we try and solve quadratics is we try and get rid of fractions, but here's no fractions here. And then we try to factorize, and we see, can we factorize? Well, I'm looking for factors of 9. What are the factors of 9? Well, it's 1 and 9, because 1 times 9 gives me 9. 2 and nothing, so it's 3 and 3. And that's all the factors of 9. So which set of factors can I add to get a value of 6? Well, if I add 1 and 9, I get a value of 10. If I add 3 and 3, I get a value of 6. So what I essentially want is this set of factors over here, 3 and 3. So I open my brackets and I say x and x, and I say x and x, and I say this value over here told me that the factors are going to be 3 and 3, and if that is positive, both factors must have the same sign in it. Now, using the zero product property that you've seen in previous videos, we now can solve. We can say, therefore, x equals 3 or x equals 3. Now, if you look at this, isn't 3 and 3 exactly the same number? And now we've actually solved for the roots, and we can say that these roots, the roots are equal. These roots are equal. In fact, there's only one set of roots over here. These two roots are equal. Now if we go and look at this actual graph and see what it looks like, we can see that this graph looks like this. That's this curve here, x squared minus 6x plus 9. And what does that look like? Well, that looks like this. Just see. It touches at x equals 3. This is the line. This is the x-axis, and it touches the x-axis at 3. And as you can see, it only touches the x-axis once. Now, already from this, what can you tell me? let's go back to this. You should be able to tell me that whenever these two numbers, when I solve for a quadratic and I get the same set of numbers, I get roots that are equivalent or equal. That would mean that my graph would always have its turning point. A parabola graph will always have its turning point on the x-axis. It could be there, it could be here, it could have been here, but the point is that graph will just have one point touching on the x-axis. And that's when we say that the roots are equal. The roots are equal. Okay.